Hey guys, I hope you are doing well. Myself Vivek Garke. I would like to introduce my teammate Mukesh Muwa.
Hi.
We both collaborated to do this project, which is comparison of a search-based and reinforcement learning agent in solving the game of Snake.
Here are our objectives of we doing this project. It is to design search-based learning agents and reinforcement-based learning agents to solve the snake game. We are totally designing four learning agents, which are three search-based agents and one reinforcement-based agent. We're gonna play snake game with all these learning agents. Our snake game logic depends on this. The snake grows when it eats food and the snake dies when it hits the wall or if it bites itself. At the end of at the end of doing all these learning agents, we're gonna compare between search based and reinforcement based learning agents.
Approaches. These are the learning agents we have chosen to solve the Snake game. Search-based agents are bed search, bed first search, and depth first search, heuristic search, and Hamiltonian cycle. In reinforcement learning agent, we use Q learning agents.
And when it comes to technology stack, we have used Python completely to do this project. We are using the normal Python to do the backend part, and we are using Pygame to do the UI part to show the snake, how it's consuming food, and I would like to explain about our game features and our game UI. The UI which you are seeing on the screen is an 8 by 8 size grid. So the maximum length the snake could go is 64 because the grid is of size 8 by 8. And in the grid we have created some space to show the length and the number of steps the snake has traveled to eat food. So here is the length and here is the step. The length and step covered by the snake helps in evaluating the goodness of the learning agent.
Now I'm going to talk about the bed first search technique in the Snake game. The snake travels the adjacent coordinates rather than the deepest coordinates of the game. The algorithm uses the Q data structures and append each adjacent nodes recursively and find the path of the foot coordinates in the snake game. By using this path, the snake reaches the foot coordinates in this game. Here I'm gonna show you the output. Yeah, as you can see in the left hand side, the yellow dot you can consider as a foot, and the silver line you can consider as a snake. And you come to the right hand side, you can see number of steps taken by the snake, and you can also see the number of the length of the snake is like so. Here I'm going to explain the code of the BFS in four steps. In the step one, the initial coordinates of the snake are pushed on the queue and set them as a visitor coordinates. In the step two, we are decoding the coordinates in the queue one by one, and it's all unvisited adjacent coordinates are pushed on the queue and set them as a visitor coordinates. The step two will be repeatedly do in the step three until the foot coordinates are visited. In the final step, if the foot coordinates are visited, we stopped and return the path. Here are the results of my BSF solving the snake game. You can see uh, average length is 56 out of 64, and I got like number of steps taken by the snake is 1000, and you can also see that like time taken to die is 2 minutes.
I would like to show you about DFS solving the snake game. By using the depth first search in the game, the snake explores the coordinates to its deepest level and then it backtracks until unexplored coordinates to reach the fruit coordinates in the game. The algorithm uses the stack data structure for the exploration of the coordinates and append each coordinate recursively and find the path for the snake game. I'd like to show you the output of the DFS solving the snake game. We have to change the variable. We have to set the game to, we have to set it to DFS. Yep. Now the DFS is solving the snake game. As you could see here, the yellow color one is the food and the silver one is the snake. And as of now, it's running around 200 steps and the length of the snake is 20 and it goes on increasing. Yep. And I'd like to explain you about the code. At first, I'm storing the coordinates of the position into the stack and then I am making them as visited. The next ad- adjacent unvisited coordinates are placed onto the stack recursively and set the coordinates as the visited coordinate. The step 2 will be repeated continuously until the foot coordinates are visited. If the foot coordinates are visited, it stops and traces the path and it returns it. This is normal basic depth first search and I'd like to share the results of the depth first search. The snake's average length is 52 out of 64 and the number of steps it has taken is 1050 before it gets died and the total time taken to die is 2 minutes 30 seconds.
Yeah, now elements and search based agent. The node in the graph should visit exactly only once, and it is the one of the brute force search algorithm. This algorithm is very much similar to the depth first search algorithm. In the snake game, it explores all the possible paths and eventually reaches the foot coordinates. By using this algorithm, we can explore the longest paths. There is a high chance of reaching the dead state in the game when the snake reaches grows higher. So here is the results. As you can see, like number of steps as of now is like 150, and length of the snake taken by 24 by 64 is keep moving on. So I'm gonna show my code. In the step one, the initial coordinates of the snake are pushed onto the stack and set them as a visited coordinates. In the step 2, the next adjacent unvisited coordinates are pushed onto the stack recursively and set them as a visited coordinates. In the step 3, if any coordinates are visited already, once it backtracks and changes the path. The step 2 and step 3 will be repeated continuously in the step 4 until the food coordinates are visited. Finally, in the step 5, if the food coordinates are visited, it stops and returns the status path.
Q learning. Q learning is a reinforcement learning method that teaches a learning agent how to perform a task by rewarding good behavior and punishing bad behavior. In Snake Game, for example, moving closer to the food is good and going off the screen is bad. At each point in the game, the agent will choose the action with the highest expected reward. I'd like to show you my Q learning output. Yep, at first the snake doesn't know how to eat the food and is less purposeful. It doesn't take very long for the agent to learn how to play game. After less than 30 games, it plays quite well. The Bellman equation. We are using the Bellman equation to compute the total expected reward of an action and to store information in a queue table. Selecting an action. At each given state, the agent looks at the queue table and takes the action that has the highest expected reward. It is entirely learned from the data. And like updating the queue table, after each move, we will update our queue table by using the Bellman equation. If the snake has moved closer to the food or has eaten the food, it will get a positive reward. If the snake eats its tail or a wall or has moved further from the food, it will get a negative reward. I'd like to explain my code. This is the code to select an action, and this is the code to update the queue table. Here is the average length of the queue learning. Out of 64, we got 63 for some sample, and the number of steps it has taken is 600, and the time taken is 50 seconds. Here, I would like to describe some performance metrics of all these learning agents. So, we have seen Q learning as the maximum length of a snake, and it took less time than compared to other agents. So, we have chosen some 60 seconds of time, and then we measured what how much food the agents ate. For example, the BFS had 40 food items in 60 seconds, whereas the DFS had only 30 items and the Hamilton just had only 25 and the Q Learning had 55 items. These are our performance metrics for our project, and the future scope of our project is we need to add more agents, more reinforcement agents like SARSA agents and advantage actor critic agents, and we may have to choose neural networks because they are also effectively solving the games. We would like to extend our scope in that way. And thanking you.